Okay, gang. Mass 6500. This is probably, I'm going to do everything I can to get everything in this final video. I know it's kind of scary when you guys look on Blackboard and you see like you've got 6 videos because you don't realize that maybe some of them are only 10 to 15. I think one was 17 minutes actually, but I'm going to try to just get through everything here. This is an extremely important video. Let's just kind of put in context where we are right now. We started out looking at X and Y outliers. And then we started looking at leverage statistics. And the things that we've looked at here, we've looked at, first of all, DF fits. And remember, DF fits, look at eliminating a case and seeing the difference in the predicted value for that case. The next thing we looked at was Cook's distance. Cook's distance, very similar to DF fits, except it looks at the difference in the predicted values for all the cases when the ith case is deleted. So in an essence, these two things right here examine predicted values with and without case I. Okay? The next thing we did is we shifted our attention to DF betas, and this one examined the estimated regression coefficients. And how they may possibly change with a case I being deleted. Now, guys, the new stuff I want to present here, I want to very briefly just get you thinking about inference procedures. And then the main topic here is called VIF, which is a variance inflation factor, which is extremely helpful in identifying multicollinearity. So, guys, in terms of the inference procedure, let's imagine that, maybe just role play here just a little bit. And let's say that we are trying to predict some response variable from 3 predictors. So we, by some measure, probably technology, we find the estimated regression coefficients. And we call those estimated because what these things are doing is they're estimating the parameters. Okay, so they're estimating these. And let's just say, for example, that we get into a situation where, now I don't want any more talk about betas. I want to talk about the estimated regression coefficients, beta 0, beta 1, beta 2, and beta 3. So let's say that the p-value for, we really don't care about the intercept, but let's say the p-value for beta 1 was 0.10. And let's say the p-value for beta 2 is 0.02, and the p-value for beta 3 is 0.52. Well, what we would say there is we would say that beta 2 is statistically significant in terms of predicting our response y when controlling for beta 1 controlling for x1 and x3. Now, and let's say that this includes some generic I case. But let's say we exclude the case. We find reason through DF betas, through DF betas, through Cooks, through DF fits, X outliers, Y outliers, that we should exclude the case. And let's say that when we exclude it, that the p-value for the first goes up. the p-value for the second predictor also goes up, and the p-value for the third predictor also goes up. Now, this would clearly be what I would call an influential case because it has completely changed the statistical significance of one of our predictors. So guys, there should be no stretch of the imagination that kind of situation is problematic. You know what? I've actually had it happen. I did some research. Well, I actually just assisted with this research on some autism, and we ran into that situation. So guys, let's take a look at. I'm not going to go into the inference part of it as much, but what I'd like to do is I want to kind of put our attention on a 3-predictor model. And what I would like to do in the 3-predictor model is I'd like to go back to the body fat. And I'd like to predict body fat in terms of the triceps measure plus the thigh measure plus the mid-arm measure. Okay? And there seems to be something kind of going on with this I=3 case. So what I want to do is I want to examine the model with I=3 included and without I=3. All right, so essentially that's what I want to do, and I'm going to actually do a whole lot for you in this data set, using this data set anyway. So let's go to you know, I don't well, I'll tell you what I can do. I can okay, I'll tell you what, we've got this as data, so let me just go attach data. That should get me back to my original data set with all 20 observations. Let me just check and say that the length is triceps of 20. Okay, so I'm back now doing my calculations with the entire data set. So what I'd like to do is I'd like to create a model with predicting body fat from triceps plus thigh, now plus mid-arm. So far we've been focusing solely on our model with just 2 predictors, but I want to change things up a little bit here. So guys, with I=3, our predicted model, I'm going to write this down, is 117.09 plus 4.33. And this would be, let's just call this X1. X1 will be triceps. So this is negative 2.86. And that's X2. And minus 2.19. That's equal to X3. So guys, just let you know what I'm doing over here. This is what I'm doing. I'm writing down the model. Now what I want to do is I want to come in and attach new data. And if I do new data, you can see that I'm missing the 3rd case, which is what I want. And I want to run my model again. So I'm going to call this new model 2 because I think I've already got something in there like new model. I don't want any confusion. And I'll tell you what I can do. I can actually just go up, can't I? All right. So I want to call this new model. And I can get my regression coefficients there. So here we see the y hat is going to be equal to 79.65 plus 3.32 x1 minus 1.99 x2 minus 1.50 x3. Now, what happens here is I'd like to go over here and look at the difference, because I've written these, and I'm going to give you an opportunity to get caught up here. And also I want to look at my notes for something, because I think that I see something that I want to point out, but let me make sure that make sure I'm on track here. I'm just like the rest of you. I gotta look at my notes from time to time too. So anyway, guys, when I look at this, I see quite a change in my intercept. It looks like that my x1 went up 1 complete unit. There was almost a unit change there, and there was about 3/4 of a unit change there. So there was, just based on one person being taken out of the model, there was some change there. Now, is there going to be a change in? Let me back up a little bit. Why do you think that there was that significant change in the regression coefficients? Well, guys, I have no doubt that multicollinearity is rearing its ugly head. And one thing I can do very quickly, just to see if that may be an issue, is to look at some correlations. And I look at the correlation between triceps and thigh. This is a lack of independence. Triceps and thigh contain much of the same measurement. So guys, they're giving me extreme multicollinearity problems and headaches because I've got two variables in my model that are essentially giving me the same information. So guys, multicollinearity, and trust me, by the end of this video, you will be pros at identifying multicollinearity. All right, gang. There is actually a calculation. So back to inference. There's actually a calculation that we can use. And I'm going to leave it for an exercise because I want to get on to some other things. If we take the sum from I equal 1 to n, so we're going to look at this across all cases, of the absolute value of the predicted value for I with the ith case deleted minus the predicted value for I with the ith case not deleted divided by the predicted value sub I. So you're actually looking kind of a ratio here. Multiply that by 100 and divide out by n, getting kind of the average difference, if you will, across the coefficients, or at least across these ratios. It presents to us a threshold by which we can expect inference problems. And as you would kind of expect, the threshold is 5%, but it actually works different. If in this case, if we get a situation less than 5%, then I would say no action is necessary. But if we get a value of this where it's above 5%, then I would say that action is necessary. So guys, if we make this calculation, which we could set up easily, a way to set up the summation, absolute values for a data set, if we get a value above 5%, then we very, very likely should examine the p-values with a change in the p-values for our models. Okay, but guys, that's not major focus to me. I feel like if we really want to examine p-values, we can just run different models, and you know, if we had to, we could run in models and look at the p-values and see if there's any problems. But this gives us a way, you know, as a red flag that we should investigate something like that. All right, guys, this is kind of the drum roll, please. This is kind of ending Math 6500. I know that puts a smile on your face. And what I want to look at is, well, it'd be really cool if you could see it, what's called the variance inflation factor. And from here on out, I'll just refer to variance inflation factor as VIF. Guys, this is where we get serious. With multicollinearity. Up until now, with multicollinearity, what we've done is we've examined correlation matrix in scatter plots, matrices or scatter plot matrices. You know, we've looked at the correlation matrix. And if there's anything, typically you kind of, some people say above 0.6, some people say 0.8. Guys, variance inflation factor gets serious. Okay. Now it's been a while since we talked about multicollinearity, so let's talk about it. First of all, the problems that multicollinearity give us, and I'm going to give you 4 of these. The first major problem with multicollinearity is the sign of the estimated regression coefficients significantly change oh, wait a minute, guys, let me back up here. I'm getting my thoughts screwed up. That's actually what I was wanting to do later on. I was wanting to do that actually at a different situation. Go ahead and tell you what I'm going to do. I'm going to tell you the problems, and then I'm going to tell you things that we look at as indications. So let me keep my thoughts straight here and just get on the problems. So the problems is that adding or subtracting a predictor or predictors significantly changes the estimated regression coefficients. We want models to be more stable than that. Another problem we run into is the extra sum of squares. Varies significantly. Depending on the other variables that are included in the model. And I'm pretty sure I put up a video on multicollinearity that got into that issue pretty in depth. One of the major issues in terms, I mean, the problems 1 and 2 are clearly substantial and significant, but the one that I think that gives us a lot of problems is the estimated standard deviations of the estimated regression coefficients. Becomes larger, or I would say artificially inflated, if you will, when we have predictors are highly correlated. And guys, the final problem that we get, we can have situations where we get a situation where a predictor is not statistically significant for certain betas in our model, even though a clear statistical relation exists. So we could get situations where we have things that there's clearly a relationship between maybe x1 and our dependent variable, but we end up getting a situation that kind of distorts that, where the p-value is greater than 0.05 because of multicollinearity. Now, indications. So I showed you 4 problems with multicollinearity. Now let's talk about some indications, and I'm going to give you 5 indications here. This is where I was getting screwed up earlier. One indication of multicollinearity, something that we can observe, is large changes in our B sub k's when a predictor variable or variables and or a case or cases are added or deleted. We don't want any one variable having a lot of change on other predictors. So guys, when we talk about large changes in our beta sub k's, we're talking about really significant changes, even sometimes a change in sign. Second thing, when we have p-values greater than 0.05, when common sense tells us a relationship exists. Guys, when you put stuff in R or your calculator, or you're using SAS or SPSS, whatever it may be, and you run your model and you calculate your p-values, but existing theory, prior studies, previous knowledge shows you that a relationship does exist between 2 variables, and you're finding p-values that aren't indicating that, then that's an indication that you may have multicollinearity issue. I can't even talk this through when I say it without thinking about Jeff Foxworthy, here's your sign. As I go through this, I keep thinking of Jeff Foxworthy kind of holding up, here's your sign, there's multicollinearity. Sorry, guys. The third indication that you may have multicollinearity is the signs of the estimated regression coefficients are different than you would think. And I think you see the kind of the underlying tone to what I'm trying to present here, don't throw the baby out the bathwater. R does really a nice job of calculations, but it only calculates what you give it. It's not going to calculate things and say, hey, Doug, you got a multicollinearity issue. These are things that you've got to determine. These statistical software packages today are so powerful that they can kind of, just kind of burst through issues where we have highly correlated, and of course, we have issues with our matrices. Is what actually turns out to be the major problem. Another indication: large pairwise correlations. And the fifth thing that I always look for is wide confidence intervals. Now, all are what I would call informal methods. These are just things that you when you run your analysis and you see something like this, you're like, huh, that seems interesting. That doesn't seem like I got what I thought I should get. Don't let R dictate the way you think. Let R do the calculations, because it's your responsibility to think these things through and look for influential observations and multicollinearity to see if it may be distorting the underlying story that you're trying to tell or the underlying knowledge that you're trying to create. So guys, these are all informal. But my intent for the rest of this video is to make this very formal, okay? Now, the formal method that I'm going to present to you is called, as you would expect, the variance inflation factor. So obviously that the measurement that we're getting ready to create here, the factor we're getting ready to create here, has something to do with inflated variance. And it actually does, and it's just what I would call a very formal method for detecting multicollinearity. And what it does, it tells us how much of the variance in the estimated regression coefficients that are inflated compared to if the predictors were not linear related. So guys, what it does, it kind of creates a threshold or a baseline, and it says if the predictor variables were not at all linear related, by what factor does the variance in the estimated regression coefficient increase due to the fact that the predictor variables are linear related, which is essentially, at the end of the day, the definition of multicollinearity. So guys, because of that, if we variance inflation factor is, at the end of the day, nothing more than a ratio. Again, you take the baseline as being the variance if the predictor variables were not at all linear related, and then it looks at how much the variance increases, and it creates kind of a ratio. So guys, if our VIF is equal to 1, that says that the variance inflation factor is 1, so irrelevant, because the variance that we're measuring is inflated by a factor of 1, telling us that we are not in a situation where our predictor variables are linear related. There's no correlation. These predictors are not correlated. The variance that we have, if our predictor variables were not linear related, is essentially the same thing we have with our model. Now guys, this is ideal. That's what you hope for. The next standard that we take a look at is between 1 and 5, and I would call this a moderate correlation. So our predictor variables are moderately correlated. It's my opinion that there's no remedial action that needs to be taken here. I would report if I had a variance inflation factor of like 4, I would report it, but I wouldn't necessarily take any remedial measures here. A variance inflation factor above 5, well, I'll tell you what, let me write it this way. 5 or higher, but less than 10. To me, this indicates highly correlated action possible. And guys, if we get a variance inflation factor, greater than or equal to 10, I think most of the literature agrees that we have an extreme multicollinearity issue, and steps need to be taken to address that. Now, guys, what we ultimately end up getting when we calculate these variance inflation factors is we get these for our variables, and we'll get and I'll go through an example of that in just a second. Now, we talked earlier about how precise estimates are. And multicollinearity, one of the indications of multicollinearity is precision. And as I said in one of the final indications, that our confidence intervals are extremely wide. So let's say that, just to keep it very simple, our goal is to estimate mu. So we've tried to estimate mu, and we collected a random sample, and we calculated the sample mean, and we get 110. Well, 195% confidence interval turns out to be 100 to 120. And another 95% confidence interval turns out to be 108 to 112. Well, guys, clearly this one has more precision in estimating mu than does the 100, 120. Now, why? Well, it's because the standard error is lower variation. So, guys, it should be no surprise then that in studying the effects of multicollinearity, where one of the indications of that is kind of an extra wide confidence interval, that the same thing holds for regression coefficients. Well, guys, remember that in looking at the variance for our regression coefficients, hopefully there's just no doubt anymore that this is the way we examine the variance in our regression coefficients. But now I want to switch gears and talk about multicollinearity. Now, if you remember, one of the problems with multicollinearity, or one of the things that can happen that can create multicollinearity, is when we have predictor variables that are on drastically different units. Well, because of that, we prefer to work with standardized regression coefficients to get our predictor variables, with the same standard deviation, things that we can actually compare. If we're trying to compare, for example, the weight of a truck with potentially the diameter of the wheels, a wheel may be like 18 inches, and the units of a weight of a truck could be, quite a few pounds, thousands of pounds. Those would be drastically different units. So, guys, what we do is we take our B sub i's, which are the estimated regression coefficients, and we turn these into our B sub I stars, which are our standardized regression coefficients. And hopefully you remember that, right? So, guys, from this, what do? We enter in what's called the correlation transformation. Which brought in some new stuff called RXX and RYX. We looked at the correlation matrix between the predictor variables, and we looked at the correlation vector between, well, it could be a matrix, but if we have a one predictor, it would be a correlation vector between the correlations between Y and X. Okay. All right, guys. So let's do some work. So we have again that the variance of our regression coefficients is this. So the variance of our standardized regression coefficients is written as this. This part right here we refer to as our error term variance. You guys, obviously this term right here is the inverse of the correlation matrix of our predictor variables. Guys, it turns out that this, for each B sub k, and guys, up here I didn't aim to put anything there. I was getting ahead of myself. That's just our betas. That's the vector of our regression coefficients, but this allows us to focus on one. And it turns out this is equal to the error term variance times the variance inflation factor of variable, or of the kth predictor. So the diagonal element V of the variance inflation factor, sub k, is the variance inflation factor for B sub k. Guys, we can show, and I'm not going to do this, and I'm not even going to require you to do it, that the variance inflation factor for the kth predictor is 1 minus the multiple determination, the coefficient of multiple determination, when x sub k is regressed on the other variables. Now, this is kind of weird. Okay, so r sub k squared is the coefficient of multiple determination when x sub k is regressed on the other x variables. Now, let's collect our thoughts here. All right. So let's go back to an original situation where we want to be able to predict some y from 3 predictor variables, x1, x2, x3. So the first thing we would want to do is we want to come up with the regression function. So we would have y hat equal b0 plus b1 x1, b2 x2, plus b3 x3. Because our focus in multicollinearity needs to be on the standardized regression coefficients, we need to enter in the correlation transformation, which gives us a non-intercept method, or a non-intercept method, non-intercept model. With standardized regression, standardized estimated regression coefficients. Focus now is on our BK stars, our standardized regression coefficient. So now if I want to examine the variance inflation factor for the second predictor, then what I would have to do is I would have to regress x sub 2 on x1 plus x3, and from this model I would create my multiple or my coefficient of multiple determination. Now guys, this is going to be an easy place to see whether or not you did or didn't watch the entire video, because if you start doing some wacky stuff here with y, then I'm going to know that you either didn't watch the video or we didn't connect. So hopefully that's not an issue the graduate level. I wouldn't think it would be. Although, you know what, I've noticed, not exclusively over the years, but there tends to be a pattern. Let me get my paper. I'm too worried about my paper to even tell the story. There tends to be a pattern, and it's not perfect, but I've noticed, because I've been doing this so long, I've been teaching at the university level now for, 25 years, 23 years, I guess, 23, 24 years, is that it seems, and again, this isn't a perfect, steadfast rule, but it seems like the professors who were the biggest slackers in graduate school are the hardest on their students. And the people who are the most highly motivated in graduate school tend to be less, I don't know, don't quote me on that one. I know you will. Okay, but I've just kind of noticed that. I would never make a statement based on one person, but the one person I'm thinking about, a colleague of mine, no longer, but and I'm not even going to talk about the gender, so I'm just going to say he, she, was the biggest slacker you could ever imagine in graduate school, and he, she seems to be the hardest on their students. So, all right, gang. The beauty of the variance inflation factor. So the beauty of the variance inflation factor for some particular B star sub k, it allows us to tap into the difference between our estimated regression coefficient and what we're actually estimating. So it gives us an estimate of the difference in these two values. And my friends, that is a powerful, powerful tool. Well, boys and girls, we're almost done. We're going to look at some cool stuff in terms of an example. But one more thing I want you to be aware of. What we'll typically do if, for example, let's say that we have a data set where we're predicting y from x1, x2, and x3, then there will be a variance inflation factor for the first variable. There will be a variance inflation factor for the second variable, and a variance inflation factor for the third. So I would call, we'll have values for each of these. Guys, we can clearly, in this case, get the mean variance inflation factor by taking the sum, I equal 1 to k, of the variance inflation factors for each of these, divided by k. And what's really cool about this, getting the mean, is this tells us how many times the error sum of squares is inflated compared to if the x variables were uncorrelated or not linear related. So let's say that we end up getting an average variance inflation factor of 50. Then we could say that the error sum of squares is inflated by 50 times compared to what if it would have been if our x variables were uncorrelated or not linear related. So it tells you, hey, here's the perfect error sum of squares. If your predictor variables weren't correlated, or was completely uncorrelated or not linear related, then you can multiply by the mean VIF and get the sum of squares that you've got. So this is achieved. This is ideal. And it tells you by what factor that the sum of squares error that you have was inflated from the perfect case. Well, guys, let's have some fun. This has been this has all been kind of crazy, you know. So let's examine some stuff. All right. Now let's see. Let's guys, I'm losing my mind here. What's going on? All right. Tell you what. Let's get out of here and let's go over here. And what I want to do is I want to start focusing on this current model called the new model. Okay. Now, guys, again, the new model is predicting body fat from triceps, thigh, and mid-arm. All right. So I see that I have a potential multicollinearity issue. I think that's pretty convincing. So now I'd like to get into all the fancy stuff that we've done. And the very first thing I'd like to do is I'd like to look at the DF fits. Now you're probably sitting there thinking, oh my gosh, we have to go through all those calculations, don't we? No, you don't. Turns out in R there is a, well, I'll tell you what, I want to do this, DF fit. There is a command. And I ran the new model. And DF fit will give me all of my values. Okay. Okay, gang, I got problems here. I don't want to do that. I'm running this on new model, and new model was created. All right, I don't want to do that. I want to do on the entire. Yeah, let me make sure I've got all cases. All right, cool. Now that's much better. Now I just want to make sure that I'm running my model on the right thing here because I'm going to be using it like crazy. So I want to predict body fat from triceps plus thigh plus mid-arm. And look at the model coefficients. All right, good deal. Now, I want to come up with my residuals. I want to come up with my fitted values. But now I'd like to get into some influence diagnostics. So the first thing I want to run is DF fit. Oops. I think it'd be cool if R would have a kind of a correction or a kind of a, if you get something close, it should come up with like an error instead of saying, I can't find that. It should say, well, you should consider D fits because it's similar to what you, okay, sorry. The next thing I'd like to do is get my DF betas. And I can do that by, I'll tell you what, next thing we did was Cook's, wasn't it? So let's run Cook's distance. Of our model. The next thing I want to run are the DF betas. of our model. And the next thing I'd like to do is I'd like to be able to run my variance inflation factor. Now, I'm going to go ahead and run this and show you what happens. If I go VIF of my model, this is pretty irrelevant because the variance inflation factor looks at the relationships between the predictor variables. And this clearly includes my Y variable, but I can go ahead and run that, and I see that it cannot find that. Well, it didn't do anything wrong, because for me to run VIF, I have to install a package. So I'm going to go install packages, and the package that I need to install is FMSB. Now, first thing it'll do is ask you to choose a crayon. I like those UCLA folks. Never met them, but I still like them. All right, the next thing I want to do is access the library for FMSB. And we're now ready to go. Now, it's tempting to go VIF model, but that really doesn't give me much. It gives me 5.03. Remember, variance inflation has to do between the variables. So the first thing that I would want to do is I would want to look at kind of step back before I get into this variance inflation factor stuff. I'd like to just step back and look at a new data frame that has my residuals, my fitted, my DF fit, my cooks, my DF beta, and so on and so forth. So I'm going to call this my newest data, and I'm creating a data frame from. I want my response first, followed by the predictors, followed by the fitted value, followed by the residual. Then I'd like to come in with my DF fit. Then I'd like to come in with my cooks. And then I'd like to come in with my DF betas. Now my DF betas, I'm going to have 3 of those because you have one for each of the predictors. All right, what's going on here? This is weird. Newest data optional equal true, cannot correspond to a data frame, cannot coerce class function. What's going on here? Well, why not? All right, okay, that should be DF beta. And I called that cooks, defit, resid. Let's see if that works. Okay, there we go, I had a typo. So guys, my newest data, let's see what we got here. We've got things kind of nice, compact. Look at my residuals. You know, don't forget, don't throw the baby out the bathwater here and forget the diagnostics. For example, I may want to look at a residual plot of the residuals over my each of my x's. No problems. No problems. Guys, I got that backwards. This should be plot, my bad. The X should go first. It's not going to matter, it's still going to be random. So we should, what was it, mid-arm, resids, and I see no problems. The next thing I'd want to do is I'd want to come down and look at my DF fits. Now, if we think back to DF fits, what were our major concerns there? Well, our DF fits, we didn't want to see anything much above 1. We got a small data set here. Case number 3 provides a little bit of concern. It's not much above an absolute value of 1, so I would not consider yet running my model without case 3. Cook's deals with percentile. Now, what I would want to do here is I would want to understand that my degrees of freedom for this are k plus 1. So what I'd like to do, just to let you know what's going on here, is I would like to find the F distribution. I can use that called QF. I'd like to find the value in this distribution that's at the 50th percentile, because if I recall correctly, for Cook's distance, the 50th percentile was where we raised concern. Remember the first degree of freedom is k plus 1, so we have k predictors. Plus 1 is 4. And the next thing we have is n, which is 20 minus 3 minus 1. So we have 16 degrees of freedom for the second degree of freedom. So what I'm looking for, anything that has a Cook's value above 0.88 is reason for concern. And as I look down through here, I don't see anything that comes even close to 0.88. The third case seems to be the largest, again, I believe, just by eyeballing. I've got another one down here. No, that's the DF betas. All right, guys, the DF betas, something we just looked at. This is the DF beta for the x-intercept. Not as, well, actually, not the x-intercept, but the y-intercept. But triceps, thigh, and mid-arm, these are the DF betas that I am most concerned with. And guys, our threshold on the DF betas with a small data set was equal to 1. And as I scroll down through the first predictor, I don't see any problems. As I scroll down through the second predictor, I don't see any problems. And as I scroll down through the third predictor, I don't see any problems either. Now, let me check one more thing, because I see a potential issue here that I may want to talk to you about, and then I may not want to talk to you about. Let's, all right. I'll tell you what. Let's just keep it. We're running out of time, and I don't want to be one of those guys who just throw stuff at you at the last second. So, now a small data set. We look at our DF betas, and nothing emerges over 1. So I really don't see any problems per cases. I don't see any reason to be concerned with the cases. Now, do we have any multicollinearity issue? Well, the first thing I would want to do is I would want to look at the variance inflation factor. Let's see, I forgot how to put this in there. I don't think this is going to work. x1 as a function of x2 plus x3. No, doesn't work. Guys, hold on just a second. I've got to do some homework here. I forgot how to enter in the variance inflation factor. Well, God, I just had that. Hold on just a second. All right, guys. I'm sure you're sitting there screaming at me. All right. I got so caught up in calling these x1, x2, x3 and forgot that R isn't calling them x1, x2, x3. So what I have to do is I have to get each of my predictors in terms of the other predictor variables. So what I got to do, I'm going to call this, this is going to be my first variance inflation factor for the linear model, where I take x1 predicted from thigh and midarm. Now, my next variance inflation factor that I want to do is from a linear model of thigh as a function of the other two. And the last variance inflation factor that I want to do tell you this stuff, all of it's hard to keep straight. I'm somebody that likes to, I've always liked to present lectures without looking at my notes. And I have no problem, Calc 1, 2, 3, the undergrad stats, but that policy I have is much more challenging. And in fact, in most cases, I can't do it, just as you saw here. I had to go find my notes and look at it. So, guys, considering that the threshold is 10 for serious concerns for multicollinearity from our variance inflation factor, I would say that we got some major issues, don't we? We could have estimate the mean variance inflation factor. By taking obviously these numbers, and I could have saved those. And so the mean of my variance inflation factors for the predictors is 460. Yeah, this is insane. This is saying that the sum of squares error of our model is inflated almost 460 times what it would be if we had perfectly uncorrelated predictor variables. And I just got to tell you, I gotta see what's going on here. What did we call model, right? Yeah. I've got to just run the ANOVA model just to see. So our sum of squares error is 98.40. If we had perfectly perfectly uncorrelated predictor variables, our sum of squares error would be 0.22, well, 0.214. can you imagine how much better your model would be if you can take all of that unexplained error and distribute it up here across the model, which is explaining the relationship. So we're getting in a situation here where I don't believe any of this stuff. I don't believe that. I don't believe that. I don't believe anything, because we have such extreme case of multicollinearity. And I think I told you probably 10, 12 videos ago that, I wanted this body fat example, this data set to stay around, because it really kind of pointed out what not to do. And so, guys, there's some major issues here. Let's look at the correlation over, and it looks like the biggest problem is between thigh and triceps. So yeah, we need to throw one of those out. The one I would throw out would probably be, I'd probably throw triceps out, because it is most highly correlated with the other one. So I would probably look at my model here, just try to predict body fat from mid-arm and thigh. And let's just see what the variance inflation factor looks like. It's going to be pretty easy. We're going to take linear model of mid-arm from thigh. So now that's right at 1. And then take thigh over mid-arm. Well, I mean, duh. I'm going to get the same thing. Yeah, so, this situation, you got a much more stable model. And I actually believe this stuff. Mid-arm doesn't turn out to be a statistically significant predictor, but your thigh measure seems to be when controlling for mid-arm measure, seems to be a very good predictor of body fat. Well, gang, I tell you what, I'm done. I'm tired. I'm done. And it's been a long semester, and I'm ready for a break. All right, take care.